Another very important concept that's going to appear throughout biology is acids and bases. In particular, when we talk about our blood and when we talk about our reproductive system and when we talk about our digestive system. So here, we're just going to make sure we have a little reminder of what acids and bases are. Okay, so we start with acids and bases. And I'm going to switch my pen colors. I'm going to start acids with red because they turn litmus paper red. They are typically sour. Not that you should go around tasting everything to see if it's an acid or a base, but things like lemons are examples of acids. They are said to be tacky. This does not mean they dress poorly. Tacky means they're almost sticky. And sticky isn't even really the right word. It's more like if you think about a lemon and you put it on your hand, your fingers become like squeaky clean. They kind of tacky and can slide along each other in a rough way. Okay. Acids have a pH, this is very important, less than 7. And they're typically represented in formulas as H, A, H for hydrogen, A for acid, and that's just a generic formula. And the reason they're written like that is because all acids contain hydrogen, that's what the H is for, which is released as a hydrogen ion. H plus in aqueous, which is a fancy word for water, solutions. Now we can compare that to a base. Okay. If you remember your Science 10, or you've had Chem 11 or 12, this shouldn't be terribly difficult. Bases turn litmus paper blue. They are said to be bitter. If you've ever had the misfortune of having your mouth washed out with soap, you will be familiar with that concept. They are slippery. Again, try and catch that bar of soap. And in contrast, they have a pH greater than 7. And you can't mix these two up. You have to know that. Their generic formula is represented for B for base, OH for the hydroxide ion that they produce, so bases will typically start with some sort of metal attached to a hydroxide, and they contain hydroxide ion, OH negative ion, which is released in aqueous solutions. Now, for those of you who have Chem 11 and 12, you might take exception with this definition of acid because you know about hydronium ions. But for the sake of what we're doing in Biology 12, this basic understanding will be sufficient. Now, if we look at this, acids and bases, neutralize each other. Now this is important because it's one of the ways our body helps to regulate acid and base concentrations. So a neutralization reaction, I'm going to abbreviate reaction, RXN. If you're going to forget that, the first time you write it, put it behind in brackets. But we're going to use it so often, I'm not going to write reactions out all the time. So neutralization reaction is something simple like you have some sort of acid, HA, plus some sort of base, BOH, and they react to produce HOH plus Ba, where this is acid, base, HOH really is just water, and Ba is what we consider a salt, where B would be a metal giving up electrons to become positive, and A is a nonmetal, which is taking electrons to become negative to form an ionic compound. All salts are ionic. If we want to do a more particular example, we could look at hydrogen chloride, HCl, plus sodium hydroxide, rearranging to form H2O plus NaCl. Okay? So that's just a basic introduction to acids and bases. But we've referred to pH here. Acids, pH less than 7, base, pH greater than 7. So we need to understand what is the pH scale. Often people forget whether acids have a high number or a low number, and the easiest way to remember it is you start counting 0, 1, 2, 3, 4 up to 14, and you start your alphabet A and you progress to B. So acids start on the right hand side at 0 and acids on the left hand side, I always get my left and right mixed, and bases are on the right hand side. Okay, and right in the middle, that's where we're neutral. Okay, and how the pH scale works, it's a bit of a trick. So a pH scale, simply pH measures concentration of H plus ions. Okay, really, we could say it measures the acidity or basicity of a solution. But what makes it difficult is that a pH scale is what's called a negative log scale, and not many of us actually understand what a negative log scale is. Negative log scale. So how a negative log scale works is if you have pH 1, what it really means is a log scale is something just to the base of 10. So it means 1 times 10, and because it's 1, it's to the power of 1, but it's a negative scale, so it's to the negative 1. What that really means is 1 divided by 10, or 0.1, and we're going to use that molar measure of concentration, H plus. pH 2 really means 1 times 10. It's a negative log scale, so we put the negative there, to the power of 2. Okay. Well, that's simply 1 divided by 100, or 0.01 molar concentration H plus. We'll just do a couple more, make sure we have the pattern. pH 3, we'll do pH 4, and we'll go all the way to pH 5. So 1 times 10 to the negative 3, 1 times 10 to the negative 4, 1 times 10 to the negative 5, which 1 over 1,000, or 0.001 molar, H plus, 1 over 10,000, 0.0001 molar, H plus, or 1 over 100,000 equals 0.00001 molar, H plus. Hopefully now you can see as the pH number gets bigger, the actual concentration of hydrogen gets smaller, meaning it's becoming less acidic. Okay. Each jump in pH number, whether you're going up or down, is a 10 times difference. So, for example, if you move from pH 5 down to pH 2, okay, you increase acidity because you're getting a lower number, more acidic. 10 times for each jump, so that's 1 jump, 2 jump, 3 jumps. That's going to be 1 followed by 3 zeros, 1,000 times. Or you decrease, you could also say, basicity you're becoming less basic, again, by 1,000 times. That's how the pH scale works. At the end of the day, the most important thing for you to remember, acids equal low pH. Bases equal high pH. You absolutely must be able to keep those two intact in your brain. So what is the standard healthy pH of certain substances or regions within our body? Remember, body always attempts to maintain homeostasis, so it has mechanisms to keep them at these pHs. And the key ones are your stomach, approximately pH 2, which means it is a, that's right, acid. Okay. This is necessary for digestion. Our tears, approximately pH 7.4. You mess with that pH, in particular getting soap in your eyes and turning it basic really stings. Saliva, well, unless you've been eating something funny, your taste in your mouth should neither be basic or acidic. Therefore, your saliva has a neutral pH of approximately 7. In contrast, our blood has a very slightly basic pH of 7.4. And if it varies from this, our body has mechanisms to bring it back to that. Our pancreatic juices, in contrast, are used to neutralize our stomach juices as they reach our small intestine, which means if they're going to neutralize an acid, they must be slightly basic, and they have a pH of approximately 8. And finally, our urine typically has a pH of approximately 6.8,